So begins another DraftScience video production and such. This one's sort of different. I'll call it a response video to Franklin Hu of the CPNSW, whatever the hell it is. Anyway, the Saturday chat loonies, I mean scientist types. Anyway, yeah. So the subject of polarization came up, and I think they ought to do just subjects. But anyway, and the idea is, what do we really, how does it really work in terms of light polarization and radio waves? So we know they're basically the same thing, same kind of stuff, generally speaking. And what's polarization? So see if we can get a response of some kind out of Franklin in terms of dealing with the evidence that exists. So the idea is that we have the two kinds of sources. I guess we could start with is this idea of radio and light. I don't even know how to. The idea of light, would be electrons producing photons in any one of a few directions, and the photons, right? And then light would be, the idea is that all of the frequencies are in parallel, like it's bands of what I would say of dots, bands of dots that come off the antenna, blip, 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 and you're making the frequency deliberately. Light, you don't make the frequency deliberately. The electron takes care of that for you. You stimulate with some electricity, and you cause something to break down in some way where it excretes the photon. And again, the photon can not necessarily is very directional, where you could argue that the radio stuff is pretty directional. The antenna shoots it off, and yeah, it spreads off the antenna in these directions and all that stuff, but it's generally speaking. So there's a subtle difference between the two. One is caused by an atomic reaction in terms of an electron shooting. I would say electrons are also shooting in this case, but it's also much more sequential, much more whatever. Alright, so you have those two differences. Subtle, but probably important in some respects. So the evidence on polarization. So one piece of evidence with radio is the fact that if I have an antenna in this orientation and I want to see if I can pick up as much of the radiation off a radio signal as I can, then I have to have the antenna configured in the same direction. And you could argue, so if I want to create a plus and a minus voltage and light a light bulb, let's say, you got a light bulb here. If I want to light that light bulb, it'll get brighter the more oriented to the antenna I put my receiving antenna. So if the receiving antenna is in the same orientation, I'll receive more energy. And I would argue that's because of the nature of the antenna. The antenna is creating energy, like this. And if you put the antenna this way, you won't get any of this or this. And all you'll get is that one ray that is in the same orientation as that antenna. So that's why you don't receive much of the signal, is because you're basically, the signal's going this way in the 3 dimensions, and you're only collecting this one narrow slice of all the energy. So all of this energy and all of this energy doesn't get to the antenna, where if it's vertical, then it gets all of this. It still doesn't get this, and it doesn't get that and all that stuff, but it gets a lot more of the signal. So that's the simple explanation for why orientation matters, okay, in radio. Now the idea of the filter in, let's say, radio and light are going to be the same explanation, but the idea is that this energy, okay, the stuff comes out, and it's polarized somehow. So we know that well, we'll just do it. So you can put a filter in front, bars, and that can destroy the signal, half the signal, from getting to your receiver, whatever your receiver is. All right, so half the signal. So the idea is that half the light has something, and half the light has something else, and whatever this is, it'll block out 50%. All right, and I'll block out the opposite 50% if I put the filter this way. And these are just general terms in the sense that it isn't really 50%. And the filter itself degrades the light. It's hard to make a perfect filter. In radio, it's still not perfect. But the idea is that you could put multiple filters, of the same kind, and each one will degrade it by 5 or 10%. So you'll lose 5 or 10% even with filters after this that are the same. So the filters aren't totally benign. They do degrade what you're going to get, the byproducts. Well, anyway, so this is the simple idea that light has a feature of polarization, that there's some idea that it's traveling where it can go through bars, and then it's traveling where it's going to get blocked by the bars. That has some orientation that dictates that byproduct, that product. All right. So that's sort of a simple explanation. And so I would argue that 50%, so if we stick with this idea, so the conventional view of the photon is this, two waves. Well, I didn't do that too perfectly. I should have done them in different colors, I guess. That would have been the thing to do. That there's a magnetic one that's going one way, and that there's this electrical one going the other way. I didn't draw that right, I guess, but it doesn't really matter. Yeah, I drew it really wrong. This could go down here, and then we have bars. Well, anyway, it's supposed to be inverse the other way, but it doesn't really matter. All right, so the magnetic field would be this way, perpendicular to whatever the electric field is. And these are supposed to be some sort of field, and it represents some sort of idea that photons are this, that these are the nodes of the photon, and that it's doing some kind of oscillating thing in a wave. It's waving somewhere. Where I would argue that if you just drew the nodes, this is the photon. It's just bits of energy at a frequency, at a distance, okay, at a wavelength, a distance between them, like they were cannonballs. None of this stuff has ever been found to exist with a photon. Like, oh, the photon's getting stronger, it's getting stronger, it's getting stronger, oh, it's the strongest, oh, it's weaker, weaker. There's no variation. It comes in clumps, as Richard Feynman said, and everybody just keeps ignoring, not dealing with the statement as a statement. Yeah, I'd say you have to think about it as something that's clumpy. It's an array. There's no such thing as a photon without the frequency, and the frequency requires there to be at least two of them. And the argument is for us to see them, and that is for them to perturbate an electron, to disturb an electron, that you need maybe 5 or 6 of these things in a row for the electron to behave the way we're going to be able to say we detected a photon. And if you take one of these out or one out of here, it's not going to detect that as the light photon. It'll detect it as maybe something else, but it won't be the photon you thought you were getting. And that sort of gets into circular polarization, which I don't want to get into. So Franklin, who doesn't believe in this transverse wave, and I guess the other trick to this is figuring out what they mean by transverse, because some people think transverse means, okay, it has an orientation that way and that way. So it's somehow on this way, and it's also on this way, that kind of thing. Like it's a thing that turns on in a field of some kind in two ways, magnetic and electric. And they call that the transverse part. Other people would say the transverse part means it's doing this forward motion thing. Okay, that's one kind of movement. And then inside of that movement, it's doing some other up and down thing. Okay, and there's the transverse part. So, but whatever. We're just saying. So Franklin says, no, it's just like a sound wave. Which I still argue it's not a wave. Like Feynman, I'm arguing it's not a wave. So quit thinking in terms of waves. But anyway, so he's sort of arguing that it's not transverse, that it is just this. It's just a wave somehow. Some kind of wave that has a strength to it. I don't understand it. Just because we know that this is a different pressure here, here. And again, there's no evidence that photons, you can have like this much of a photon or, these little amounts. There's just every evidence that it comes in a clump, a quantum mechanical clump of energy. All right, so anyway, so let's get to the theory of what causes polarization. Now, Franklin's sort of implying some kind of polarization built into this amplitude or something. Like this amplitude represents the polarization. Frankly, there's no point in me trying to explain Franklin's explanation because I couldn't understand it. So we'll just tell you what we're going to argue is the real explanation. Alright, so if you understand the photon is this stuff coming at a frequency, alright, moving in a direction, little clumps, nodes of your wave. Alright. And you understand that you need a certain number of clumps for a receiver to say, I got the signal, I got it, I saw that. Okay. Then all you have to do to understand polarization is to understand that this stuff can be oriented in space a little bit differently. A little bit out of a perfect alignment. So when it doesn't come out on a perfect ray line, it's a little bit off. And the reason why it would be a little bit off is because it is being produced by electrons, and electrons in atoms are constantly moving their position, constantly happening. They're going from here to here to here to here to here to here. They're moving around. And as this energy, these photons are being produced by an electron, it might be in this position when it shoots out the first bit, and then it'll be in this position when it shoots out the second bit, and it'll be over here when it shoots out the third bit, and over there. And so and this is in both dimensions. That's the circular part, I suppose. It could be off in and out as well as up and down. But anyway, so the alignment's off, and the alignment's going to be off by a timed equation. So you could sort of understand that time would be quite relevant, and time is frequency. So you can sort of understand that the faster, the closer these objects are going to be to each other, the tighter their frequency, the less time that took place between them. That is, the less movement there was between, of the electrons. So the electrons didn't disturb them as much. The faster the frequency, the less time there is for the electron to screw things up. So you would have less polarization the higher the frequency, and the longer the frequency, the more possibility of polarization, the bigger the polarization gets. Now, that's perfectly consistent with what's seen, which is if you want to block radio waves, you can make bars that are literally, visible. You can see them. You can see how thick they are. And depending on the radio waves you're attempting to block for polarization or filter for polarization, this grating gets wider and wider and wider. So this would be like for microwaves, would be something like this. if you want to make a filter for microwaves to test for their polarization. And if they were longer radio waves, you could probably go to an inch spacing between the bars. Because the polarization is getting more and more eccentric. The more time the electron has to move between the time that it's emitting the photon, the more differential you have in the arrival of these little bits. Alright, so how does that cause the effect? So now we'll go to that. If you've followed along so far. So the emitter is the source of the polarization, in the sense that the emitter is not stationary. And that's all you really need to know. The emitter is moving, and the movement of the emitter is causing an eccentricity in the projection of the photon. Now, why does the filter... So if you wanted to filter polarization that people would say is going this way, okay, you put a filter in going the opposite way. And why does that block this? Is that the way I wanted to say it? This you'd think would get through if the bars are this way, but it actually gets blocked. To get through, it has to be, the filter has to be in this orientation. So this orientation, if I put the filter like this, and the photons are off this way, somehow this filter, okay, blocks the photon, and this filter allows it to get through. And I would argue the reason for that is because the polarization is exactly opposite what they're thinking. It's off this way instead of off this way, so they're just misunderstanding which polarization they have to start with. And the truth is that what's going to happen is as the photon comes towards the filter, let's see what's the best way to illustrate that. So just think of these bars as just lumps in the way, I guess. I don't know how else to illustrate it. So those are the bars coming in and out of the board, let's say, and you're going to shoot your photon towards them. You can sort of understand that if the photon's coming through and it has this little bit of difference, okay, that part of it can get through, but part of it won't. Okay, so this one will get hit here, so he's not going to make it through. This one will make it through, and this one will make it through, but these two won't make it through. So this one's going to hit this bar, and this one's going to hit this bar. So you've lost most of your frequency, and now you only have this 2x frequency, and then you might have another photon that has 3x of the frequency left, and then your photon ends up going from this precise thing, okay, to something that has irregular, and it's not enough of the original frequency for the receiver, for the electron that's going to get hit in your receiver to recognize the signal. Wait. So that's why the bars kill the signal, is because the bits of the photon are basically getting broken. Now there's still energy in here. I mean, when they hit the electron, they actually move the electron, so there's energy being displaced into the material, and some of the energy goes right through. That's why they don't get hot, like as hot as you would think they would get if they're blocking half the light. It's because most of the energy of that light still got through. It's just that it's gotten through in a form that can't be detected. It's not at the right frequency anymore. It's at the wrong frequency, and it won't be able to do what it has to do. As I've explained, the electron on the receiver end, to give you a quick lesson on that, needs to be hit within a certain amount of time, or it goes back to its original position. So when the photon's coming in as little cannonballs, if you hit it once, it rebounds. Okay, it goes out, and it can come back to its original position because it's in tension in the atom, and there's forces that are going to push it back. And so the problem is you have to have a frequency that it's quick enough that the second one hits it while it's here, not, when it gets back to this position. If the second bit of your energy doesn't get there before this one starts going back, then you can't push this electron another bit forward. You just end up pushing it out to here, from this point, A point to B, and then it goes back to A, and then you hit it back to B, and then it goes back to A, and you hit it back to B, and you're not getting anywhere. You're not gaining any distance. And the key is to get the electron far enough away from its proton that the force gets weaker and weaker, and the electron has a longer way to travel back. It's far enough away where the course back will take it a longer amount of time, and through that process it will release the new photon. So the idea is you got to keep hitting the electron before it rebounds, and push it out pretty far for us to say we received an electron. So you can't, our instruments can't see the electron you can't see it create a new photon, certainly, and you can't detect it as electricity. Okay, the electric effect probably takes less than the photon effect, but regardless, we can't detect unless we get a certain minimum number of hits in a row at the proper frequency. And if they're not at the right frequency, if you hit the electron too soon, well, too soon really couldn't matter much. But anyway, there's just requirements to hit it with a certain tension, because the atoms have a certain tension, and that explains why there's spectral lines, that certain frequencies are the preferential frequencies of the atoms themselves, in terms of that's defining how much tension they have. So certain frequencies are harmonic. They have the right resonant frequency, the right resonant speed to constructively add to the pressure on the electron, to keep adding new pressure, not to be, the worst thing, you don't want to hit the electron when it's moving back, because well, that's just going to undo what you did. So that's going to annihilate the force, essentially. The two are going to cancel out. So that's what they call destructive interference. So you want to kind of constructively keep adding the energy to move the electron. So anyway, that's the theory. So the basic points I would argue to Franklin that are true is that there is a ray length to photons. They're not just a wave. They're a wave of a specific amount of wave. This is what's got to happen for it to be seen. And they say for our eyeball, you need 6 of these nodes, all right, for us to see the light. We don't see it unless there's 6 of those nodes. Now, a frog only sees maybe it only needs 4 of those nodes, and it registers the light. So a frog sees light we don't see because there's pieces of light, photon, that are those short bits flying around all the time that we don't see. And we don't see them probably for good reason, because in daylight they're not very useful, and maybe it's only useful to see that extra resolution when you're very close to something. Very far won't do you any good for your far away vision. Everything gets too light, too white, too gray. So our eyes are tuned to the world we live in and the distances that are important to us, where a frog's eyes are built for the world it lives in and the distances that are important to it, which are close up and in very dark circumstances. They need to see at night. So they need to see every bit of light and all little bits of light. But there's probably more little bits at night. More scattered light. Scattered light would be light that could be potentially broken, more broken. So they need to see those bits of scattered light. All right. Is there anything else? So polarization is basically being called. So we know the fact is that you need a length of the ray. So whether you think it's a stupid wave or not doesn't matter. I'm just saying you need a certain number of humps in the wave, so you understand that part. and that the argument would be is that what the polarizing filter is taking advantage of is that the rays are not on a perfect line. They're a little bit oriented, and that's the nature of the polarization. And the longer the frequency, the more the more time there is for this orientation differential to be larger. Okay, so there's more variation. So X-rays would be really close to this line. Visible light would be a little bit wavy, and radio waves would be a lot more wavy in terms of the out of alignment. So the first argument is that you have to have rays. The second argument is the rays are out of alignment, and that the key to filtering the light is basically breaking the light. It's not like you're filtering it, like the energy hits the filter and 50% reflects. We don't see any reflection off of polarizing film. It's not very reflective. So obviously the light that isn't getting through isn't reflecting. So 50% isn't bouncing off and flying somewhere else. We know it's going into the filter in a sense. And we also know that the filters don't get extremely hot. So obviously not all of the energy is getting burned up inside the photon's energy isn't getting absorbed and making the plastic hot. So we have to concede that some portion of the energy is getting out. All right, and it's just in a form that we can't see. It's broken. It's gravity, essentially, I would argue. It's been broken back into gravity again, because if I take this out and I take this out, I've got a different frequency, essentially. So maybe there is some, maybe they could take a light polarizer, and if they could put enough light into it, they could pick up some radio waves that are actually being produced, when you break the photons in a consistent way, which would happen now and then. You'd go from the nanometer scale to like a microwave scale and get a few microwaves out, by breaking the photons just incidentally in proportional ways, where before you had this frequency and now you have this frequency, and theoretically you could have even bigger frequencies. And so they're all kind of harmonics of each other, theoretically. Alright, so that's probably enough on the subject of polarization, right? So again, back to the summary. The photon comes in clumps, clearly, humps, whatever. There has to be a certain length of those clumps at the consistent frequency for us to receive the energy, either as light or radio waves. Our receivers are very selective. They only see a certain band of frequency. And if you break the frequency, we're not going to register that as a photon because it has a break in the frequency. It needs the whole 5 or 6 of them. And if it doesn't get 5 or 6 of them at the right frequency, it won't see it. And based on that principle, you can understand that if I just take that out of alignment, I'm going to create some kind of idea of polarization. And the fact is that each individual photon can be polarized in both directions. So it can be off-center in both ways, and so it's circular. Like each one isn't... See, they sort of say that from sunlight that one photon is polarized this way, and then one photon is polarized this way, and then one photon is polarized that way, and one is this way. And to some extent that may be true, but they can also be polarized in, these ways, where it's off of that center. It's going, one hump of the wave was here, and then one hump was here, and then one hump was here, if you can understand, but it isn't necessarily true, just because usually electrons are in atoms, and the atom has I should just draw that better. you could argue that the atoms have a configuration like on the surface. So the surface argument's a good argument. Like the surface of something, the electrons are in a certain orientation. And if I put light in at certain angles, I'll force the light to come out in a polarized, in a one orientation. So it comes in going all kinds of ways, all right, and it leaves going one way, having one kind of polarization. And I would argue that that's because the electrons are going to be hit in the same, usually the same orientation, so their wobble's going to be in these directions. And so their movement's going to be more likely they're going this way than they're going this way. And so when they reflect the light, they're going to reflect it from different positions. They're moving. And so the polarization is going to be in that one direction more than it's going to be in this direction. So it came in going this way, wobbling this way and this way, in terms of having out of being out of place in the two dimensions, you know, in and out, a little bit out, and then up and down, a little bit out, and then it'll come out being only moving, or being out of alignment in one way, rather than being out of alignment in both ways. And that just depends on this angle. And the sharper the angle, the more likely the light comes out unaffected. But the sharper the angle, the more likely it is to be polarized. And that's why glare usually is at these sharper angles. And that's why you can filter it out, because it has a specific polarization to the ground that's flat. The surface that you hit is likely going to have to be perpendicular to your view. Is there any other polarization details that I need to cover? I don't think so. So I think that explains it. It doesn't have anything to do with magnetic fields and electric fields, or photons aren't. This is not a magnetic or electric object. I would argue that photons, from my theory, are black energy. That is energy that only affects electrons, in terms of it only gives electrons momentum. It doesn't give a proton momentum. So if a proton got hit by a photon, all the proton would do is say, that's black energy, that's electron energy, I just divert that. Okay, so I take energy going this way and I'll make it go that way, or this way or that way, perpendicular to where it went in, and it won't affect the protons, won't give the proton any momentum. Where in the case of the electron, when the little bit hits, I'll explain that real quick. Just throw it in as a bonus, even though I've been over it a million times. The electron has already inside of it energy. Okay, and what it does is when something comes in, it exchanges. There's always a reflection. The bit, and what's basically happening is a bit in here, an arrow, bit of energy going this way is released, and a bit of energy this way takes its seat in the boat, and now the electron has a momentum in this direction. But that's all that's happening. And for electrons to emit photons, they have to be given enough movement where they, when they come back, they do the same thing. They reflect the energy they're absorbing. So to come back, they essentially have to absorb energy, and then absorb energy, and absorb energy. And when they absorb it, they released something going the opposite way, and that's your photon. So when light reacts with an electron, it is absorbed by the electron and then re-emitted by the movement of the electron, the rebound of the electron. So it is technically a new photon. A photon doesn't technically bounce off of electrons, but it can technically appear to bounce off of a proton, you could argue. So the proton diverts the energy, so if it comes in this way, I should draw it the right color. It will reflect it, perhaps that way. So that's sort of the interesting part. I won't open that can of worms. But the reflections like glare might even be caused by protons, but I don't want to get into that. That's a level deeper than this explanation needs. So anyway, so the basic idea is you need the ray length, and the point is the ray is got nodes out of position, and that's polarization, and that it's more out of position the more time you give it. More time equals more, gotta use greater than, the more, whatever you want to call that, displacement, out of alignment. And that the filter is basically just killing nodes. Nodes die in the filter, and then only part of the energy gets out of the filter, and part of the energy goes into the matrix, the substance of the bars. The bars absorb the little piece of energy. And that's the explanation for the phenomenon of polarization. What I would argue is the correct explanation, and I can't even give you their explanation because it doesn't make any sense. It doesn't explain anything at all. It has some idea that somehow because the photon is a snaking, that somehow they all, even though they're a different phase, so I have a bar here in the way, and the idea is the snake comes in and he snakes around the bar, you know, and just happens to be that his wave just happens to go around the bar. But the problem with that theory is that if I just change the phase a little bit, you know, I move the lump over a little, or move it over a little more, obviously it's not going to go around then. So different phase light should get blocked by the bar, and that's not found to exist. Light out of phase doesn't get affected by the filter differently. You can't phase the light to make it go through the filter and then change the phase and make it get blocked by the filter. So their argument is nonsensical, and it has in it also, I guess, components that don't make any sense. Now, another thing that may be true of some of this is like, say, when you do a radar experiment and you have the filter very close to the antenna. I shouldn't even bring this up because it really probably has nothing to do with it. But the point is if your transmitter is very close to the filter could be, actually, the electrons on the filter could be affecting the electrons that are going to be emitting the energy, and they could be actually pointing those electrons right at the bars because they're metal, and you know, because these are metal bars. I don't know whether it works with bamboo or some other substance. I haven't seen it done with non-metallic objects. So in some cases the effectiveness of the filter might be just based on the fact that the transmitter is actually being affected by the existence of the metal, and it's affecting the electrons directly before the light's even emitted. It's being pointed right at the bars, that kind of thing. But I don't think that has anything to do with it, so I shouldn't even have thrown it in. So never mind, I said, never mind that part. Alright, so we're back to, it's clean. Alright, so we'll call that enough of a video. Let's see if we can provoke any kind of response on this one subject of polarization, and some sort of, I would argue, a rational, mechanical explanation for the phenomenon versus the conventional, what the hell? The conventional that I can't even really describe because it doesn't make any sense. So there you go. And but they keep asserting it as if it's all true. I mean, you know, they just make the state. This is what it does. This is what it does. No, it doesn't. So anyway, till next time. That's not what I want to do. This is probably the one I want to do. Yeah.